Thanks, Joe. Good evening, everyone. Thanks for coming. So as Joe mentioned, anomaly detection has been actively researched. In fact, last week during the Strata conference, there were talks from Microsoft and Netflix on their approaches to anomaly detection. We also have been working on this problem for a while. So it was nice of Nick and Joe to give us this opportunity to share what we have learned so far. So my colleagues Vijay and Jenna are going to present what we have developed at Twitter. We are part of the data fidelity team at Twitter, and which in turn is part of the data platform umbrella. We serve teams across the board, be it product, be it infrastructure. So we deal with metrics, both system metrics as well as application metrics and business metrics. So to probably say the obvious, today real-time communication is one of the key aspects of internet, be it the web or the mobile. And real-time communication is not limited to a particular domain, be it tweets from space, or you want to get real-time updates from Grammys or the ongoing World Cup cricket. In fact, governments around the globe have flocked onto Twitter to serve the citizens. So very recently, the Australian government has started to use Twitter to warn their citizens of any possible sightings of sharks on the beaches. So as we all know that in the consumer space, it's really important to deliver great content, and at the same time, the performance and availability of a service is equally important. So we live in an age where the decision making is typically data driven. So data fidelity in this context is of very key importance. Now, ensuring high data fidelity is very challenging in light of hundreds of A/B tests we do on a routinely basis and the agile development methodology that we have at Twitter. Also, we have several data partners like Nielsen and DataMiner to give you a couple of examples. So it's absolutely critical to ensure high fidelity data, because these guys make decisions based on the Twitter fire hose. And last but not the least, as I mentioned earlier, that from an operational standpoint, it's very important to ensure high fidelity data to guarantee high performance and availability. So there are various challenges when it comes in the realm of data fidelity. Presence of anomalies is one of the challenges. Now, anomalies routinely occur in production data due to a variety of factors. Broadly speaking, one can classify these factors as exogenic or endogenic. Exogenic factors include user behavior or events, such as Oscars or Super Bowl. Who could have expected a blackout during Super Bowl a couple of years back? And of course, the famous selfie from Ellen last year, which generated a lot of interest. And endogenic factors include the agile development cycle we have at Twitter. And time to time, we do bump into data collection issues. So that how do we filter out data collection issues from true anomalies? And last but not the least, at Twitter, just like any other big internet company, we monitor millions of time series. So how can we scale anomaly detection to a large set of time series? Now, probably the most obvious way to detect anomalies is via visual inspection, but clearly this is prone to errors, and it is clearly not scalable. And there have been previous reports which have shown that the volume of data is growing by leaps and bounds. The machine-generated data, for example, is expected to grow to 40% of the digital universe by 2020. And in the cloud infrastructure space, it has been estimated that it's going to grow by 50% on a year-over-year basis. So we invested quite a bit of time to develop algorithmic approaches so that not only we can automate and we can also scale. Now, as Joe mentioned, that there has been active research being done in the industry on anomaly detection. Having said that, the field itself has been researched for over 50 years. And we actually looked into prior techniques from various fields, from statistics to finance, signal processing, networking. Now, the key differentiator is that the reason why anomaly detection has been researched for over 50 years, that the definition of an anomaly varies from one context to another. What may be an anomaly in e-commerce may be different in signal processing. So we did evaluate a large set of techniques from different fields, and our experience was that we could not use any existing technique off the shelf for the Twitter data sets. So although I presume that the audience here would be privy with the basic characterization of anomalies, but I'll just, for the sake of completeness, quickly go through it. So there are various dimensions where you can characterize an anomaly. One is the most obvious, the magnitude. Second is the width of an anomaly, that whether it's a point anomaly or does it occur in tandem, like 2 minutes in a row, 3 minutes in a row. The next is the frequency, that is it more periodic? So you may have a cron job at 1 a.m., and if it induces a spike, you may not characterize that as an anomaly because you know that it corresponds to a cron job. And lastly, the direction. Things may go up or things may go down. So you want to characterize the direction of the anomaly, and which is very helpful for the SREs, that for certain metrics you want to capture positive anomalies, and for certain metrics you want to capture negative anomalies. There are two flavors of anomalies based on the data we observe in production. So here, as I show, that one is the global anomalies, which you can typically detect using any simple rule. But however, the local anomalies, which typically correspond to the seasonal nature of the time series, they are much difficult to capture using the traditional rules, and that is where we laid most emphasis on. So as I mentioned earlier, the traditional approaches are pretty simple, which is not to say that they are not useful. I mean, if you have a straight line, then you can use a linear regression. But for our data sets, we observed that using a rule of thumb of mu plus 3 sigma doesn't quite work, because you will not be able to find local anomalies, which I illustrated in the previous slide. And even in the context of global anomalies, there are various questions which need to be answered. Should you be using a raw time series? Should you be using a moving average? Moving average is typically used to to smooth out the white noise. Now, in context of moving averages, should you be using a simple moving average or an exponential weighted moving average? If so, what should be your window width? What should be your decay factor? So this is in itself is an open research problem, and your mileage varies depending on the characteristics of the time series. So the other key observation we made during our analysis is that the time series at Twitter is highly seasonal. So this manifests itself as multiple modes in the probability density function, so as illustrated here. Now, one may wonder, what is the implication of having multiple modes in your PDF? Well, we did some analysis. Having multiple modes, it increased the mean of your time series by around 0.2%, but it inflated the sigma by almost 5%. And as I showed in the previous slide, if you use the simple rule of thumb of mu plus 3 sigma, then your decision boundary will be moved to the left or to the right. So you may miss out on some anomalies because of the inflation of the sigma. And the multiple modes typically correspond to the seasonal nature of our time series. Further, a key observation is the fact that mu and sigma, they are themselves susceptible to anomalies. So when you use the simple rule of mu plus 3 sigma, you are intrinsically susceptible to anomalies. So there is a subfield in statistics called robust statistics, where metrics such as MAD and sigma MAD have been proposed. So we do leverage these metrics, as I will show later, to come up with more statistically robust estimates. The two common tests proposed in the literature are the Grubbs test and the ESD test. The Grubbs test is widely used if you have to detect a single anomaly in a time series, and the ESD test is widely used if you have to detect one or more anomalies in a given time series. However, there are two limitations due to which we cannot use these off the shelf. One, these tests are seasonality unaware. Second, they assume a normal distribution, which is not the case for our data sets. Consequently, we could not use them off the shelf. So what's our approach? So we try to leverage existing research and make it amenable for our data sets. So one of the first step we did in our approach is, how do we address seasonality? So there is a technique called time series decomposition, which has been proposed for over 20 years in the area of statistics. So essentially what you do is you take the raw time series here, and then you decompose it into three components: the trend, the seasonality, and the residual. So the benefit is that if you look at the PDF of the residual, so here in blue I show the PDF of the raw time series, and as you can see that there are three modes in the PDF. In contrast, if you look at the PDF of the residual, it is approximately normal. And the benefit is that it transforms a multimodal data to a unimodal data, and consequently the time series of the residual is amenable to application to ESD and MAD, and which is exactly what we do. Now one may wonder that you can use conceivably you can use the residual time series and apply ESD on it, but it doesn't quite work off the shelf. The reason is that as you can see here, when you do time series decomposition of the raw time series, you have this spurious bump in the trend, which manifests itself as a spurious negative anomaly in the residual. So you really don't want to report this because this is spurious. So what we did, we married robust statistics with time series decomposition. Well, the first step was instead of using the trend, we used the median of the time series. And as you can see here, the negative anomalies from the previous slide, they have been filtered out. Next, what we did was we applied ESD on the residual time series. As you can see here, that the anomalies here, the local anomalies and the global anomalies, both can be captured if you apply ESD on the residual. The one other improvement we did in the ESD algorithm, instead of using mu and sigma, which are inputs to ESD, we use MAD and sigma MAD, which I showed in one of the previous slides. So these are statistically robust against anomalies themselves. So here is an example of a data set from production. And as you can see, that using our approach, not only we are able to capture the global positive and negative anomalies, you can also capture the seasonal positive and negative anomalies. All right. We open sourced a standalone package earlier this year. It is available on GitHub. Some of the highlights of the package are you can filter the anomalies to the last day or to the last hour. So as I illustrate here, this is a 1 week view of the time series. And to assist better analysis, here we filter the anomalies only for the last day. And you can also set the direction. If you are interested in only positive anomalies or negative anomalies, you can set these as command line arguments. You can also turn on a flag to report expected values. And you can also apply the package for longer time series. So typically, we apply the package for 2 week minutely data, but we have also experimented with 6 months of minutely data. And for that, we came up with a piecewise approximation technique, which was presented in Hot Cloud last year. So far, it has been widely used outside Twitter and even outside computer science, so which is sort of encouraging. And if you want to know more about the package, feel free to visit our blog. Next, my colleague Jenna will walk you through the pluggable design and how we use it at Twitter.
Thanks, Arun. Hi, everyone. I'm Jenna. I'm going to give you an overview of the frameworks we use for anomaly detection at Twitter. Basically, it's just composed with two components, this data source and detector. They are pretty easy to understand just by their names. Data source is just where you fetch the data back and do the anomaly detections. Right now, we are supporting quite a few of different data sources. For example, file data source, JDBC connection, like MySQL, Vertica, and several other internal data sources we use at Twitter. When it comes to detector, that's where the statistical models live. So you may wonder, OK, what kind of detectors you are supporting right now? The answer to this question also leads to the beauty of the design. So the answer is actually, OK, any detector we want to support is pretty easy to get plugged into the system. We have a well-defined interface, so it's just pretty simple to get any statistical models plugged into the system. And same for the data source. Right now, people are using it in two different ways, library and system and the service. So when people use it as a library, people can just depend on our target and build it locally, get the results pretty quickly. And they can also schedule it as a job running periodically. At Twitter, on our infrastructure, we could schedule it as a cron job on Mesos. Right now, we have jobs running hourly, every 4 hours, or whatever schedule the users could like. And also, our framework is running as a service. User could send us HTTP requests via our RESTful API. So right now, our framework is used by roughly 10 internal customers, and this number is growing. OK, here is an example of an anomaly generated by our framework. You can see it's an auto-generated email automation notification. You can see there it has Jira integrated, which means every time an anomaly is detected, a Jira ticket will be created automatically. And in the bottom, you can see there's a plot which gives the user a visual reference of what the anomaly looks like, what the data looks like. I don't know if you can see that clearly, but the red point there is the real data. The green one is the value we predicted. And the green vertical one is the range we can accept. So obviously, the red spot is beyond the acceptable range, so it's considered as an anomaly. When a data set has multiple dimensions, it's always useful to break it down on a particular dimension or dimensions, so people can run anomaly detection on each data slice to get a better understanding which data slice could have something wrong. So in this example, the first field, client equals something. This is a breakdown on the dimension client type. So this anomaly could be an anomaly of the, let's say, Android data slice or data slice of iOS or any other clients. In terms of granularities, right now we have jobs about daily data. Something I want to highlight here is some of, I could see lots of our use cases has the has the weekly seasonality. So what we did here is we did the seasonal adjustment based on the weight of each day of the week. And from there, we applied the statistical models on the adjusted data. And based on our experiments, it improved our performance a lot. Besides that, we have jobs about minutely data. And the algorithm we used here is just what Arun talked about earlier. And by leveraging our real-time infrastructure, we also achieved real-time anomaly detection. I'll hand it over to Vijay to talk about the real-time in details.
Great. Thanks, Jenna. Awesome. So yeah, so as Jenna was saying, initially our focus was on kind of daily and hourly data, but the thing we realized is, as we sort of grow out our infrastructure, we want all these kind of core metrics in real time. And a lot of these metrics are actually produced using Hummingbird jobs. So just to give you some context about sort of how it works. So Hummingbird's a library that basically lets you write MapReduce programs as a series of either Java or Scala transformations. This is an example of something called lambda architecture, which is a term that was popularized by Nathan Mars. But I mean, essentially how it works is, you have incoming data, let's say some data on a queue, and it gets basically sent off to both batch and real time, right? So the same data gets sent off to kind of both layers. And in the real time side, you might have some sort of topology. In this case, in our case, we have like a storm topology that's computing a real-time aggregate, and that's sending it off into some key value store somewhere where that data can be easily queried. On the batch side, you have that same data, except it's pulling, it's computing the aggregates and it's writing out to some master data set, in this case HDFS. And there's also a serving layer on top of that basically pulls from that and allows you to easily query. So in the final step, when you want the answer, what's the actual aggregate or whatever it is you're looking for, the final layer basically merges both the real-time answer and the batch answer to produce the definitive one. And this offers a lot of great properties. One is tolerance against hardware mistakes and also human mistakes. And the other thing is it can support a wide variety of workloads and also provides low latency reads and updates. So the thing we wanted to add is, okay, well, at the end of this, let's plug in some anomaly detection. And the biggest issue we probably face is data integrity. So the real time is obviously constantly running, and the batch is running behind it. So there's always this lag. But what we're pulling from is the real time aggregates, and so these are approximations, right? So what we realized is we had to, if we had some data that we cached, we had to periodically update it, because as the batch job finished, it would provide the definitive answers, and so the model would be able to pull in the correct data and provide better results. And the other thing is, when tuning the model, we realized that because we're not dealing with the actual definitive data, we also had to increase our threshold for anomaly detection. So here are a few other lessons. So one of the things is the model is actually in R, and all of our infrastructure is on the JVM. So for a while we were like, how are we going to kind of get around this? I mean, and there's really no good implementation of this model in Java or Scala. So we tried a couple of these like JVM R bridges. You might see things like JVM R, Rengen, RJava. And each one had its kind of own set of issues. So either they had high latency. So if we're trying to do minutely anomaly detection, it just wouldn't run fast enough. And the other thing is that a lot of these didn't have great exception handling. So if something went wrong in applying the model, it wasn't really clear sort of, okay, what's actually going on here. The other nice thing is that as we built this out, we actually came across this really nice sort of model that we can kind of apply to all of our real-time jobs. And this actually takes advantage of the future abstraction from Finagle, which is a library we use at Twitter. And if you look at it, I mean, it's like 8 lines of code, and really all it does is it says, hey, do some work. If we need to keep going, let's sleep for a minute or whatever a period of time, and then let's run it again, and then let's just keep going. And so this really, gave us a nice generalizable model to, quickly add kind of new use cases. And the other interesting thing is that the data we're working with is all real-time data. So it's actually hard to really capture anomalies because, as the batch job catches up, if there was an anomaly, if there was a drop, well, the batch would fix it. So you don't see the anomaly anymore. So, what might be considered an anomaly at a point in time could just be the result of that real-time topology, being down or the data just not coming in. So it's hard to, so there was actually, little kind of historical data that we actually had to go off to tune the model. And so that was one of the problems we had to kind of, deal with. And all these set of challenges, I mean, there's still a long ways to go in dealing with these and others, and I mean, and different approaches to try. For example, streaming algorithms, especially if you want to look at sub-minute granularity, you want to look at system metrics and like secondly granularity, for example. The other thing is that in general, like I was saying, how do you ensure that even if the real-time topology is being down or there's something wrong with it, how do you basically make yourself robust to that, right? How do you minimize false positives? And the other thing is, well, this is we just started off with a few use cases just to kind of get the ball rolling, but there's so many more things to do. Things like looking across time series. If there's multiple time series, is there a correlation? If there's an anomaly in one and there's an anomaly in another, is that a higher indication of something really going on? And adding more core metrics as we get more of our kind of customers onto the real-time infrastructure. And hey, these are all really exciting problems. And I mean, I'm excited to be here and talk about them. And if you're interested in learning more, feel free to come talk to us. And we're also hiring, so take a look as well. So and that's all I have. Thank you.